Hello and welcome. I'm Professor Rick McDowell from University of La Verne, and today we want to go over the calculations to support a periodic inventory, also known as fixed time period model, or just a P model. You'll hear this referred to simply as a P model. Here we have a fixed time period, but a variable order quantity. This is distinct from a Q model, a fixed order quantity model, where the order quantity in a Q model is fixed, but the time period will vary. This is exactly the opposite. We're going to place an order every certain time interval to replenish this item. So here's our scenario. We have a box. This box is consumed in packaging and shipping our products, and we replenish this box every 2 weeks. So we place an order from the supplier every other week. So this is a fairly typical scenario for packaging materials. They're frequently managed on a periodic inventory model. So every 2 weeks we're going to place an order. The order lead time is 3 weeks. So from time of placement of order till the time it's received will be 3 weeks. And we need to develop a fixed time period model that determines our order quantity to tell us how much we order every time we place that order to replenish. We want to guarantee a 96% probability of running out. This is our service level or our in-stock probability. By definition, that means that we have a 4% tolerance for out of stock. In each order cycle, there will be a 4% probability that we will run out before our replenishment order comes in. Now, the first thing we need to do is make sure that we're using consistent time periods. We have consumption in weekly time periods. We have our order lead time in weeks as well, and our review period in weeks as well. If you do not have common time periods for your historical consumption, your historical demand, your lead time, and your review period, you need to convert these to one common time period. So first, let's start with what is our mean demand per time period, and that will just be the average of those historical weeks of consumption. So we see that our mean demand is about 144 boxes per week. Next, we need to know the standard deviation of demand. And we see that our standard deviation is a bit under 6 boxes per week, 5.85. Now our service level or in-stock probability, we've set at 96%. So we need to figure out a z-value that corresponds with a probability of 96%. Remember, z is our multiplier that we will use with standard deviation to achieve any particular probability of getting results within the limits and not outside of our limits. So here we want a z-value that gives us a 96% probability. We'll use the norm S in function, normal standard inverse function, and you see it's prompting us for a probability. We'll give it the 96% probability, and we see we have a z-value of 1.75. Now what we have to do here is we have to determine what I call an order up to level. Some people refer this as a max. Our order up to level, every time we go to place an order, we're going to order whatever takes us up to this number. And the equation is represented right here. Let's break it into two parts. The first part is cycle inventory. This is the amount of inventory on average we expect to consume over this time period. And the second half of the equation is safety inventory. This is the additional we will add on top of that to guarantee our 96% service level. Now, assuming demand is normally distributed, and we will assume that when we do these sorts of calculations, assuming demand is normally distributed, if we just carry the mean amount that we expect to consume over a 5-week period, we would assume a 50% probability of running out. Well, that's not acceptable. Our service level, our probability has to go to 96%. So we're going to have to add some amount of safety inventory to our order up to level that will take our probability up to that desired 96%. The formula for our cycle inventory piece is the demand during lead time plus review period. The review period is the order interval, the time between inventory reviews. So the demand during lead time plus review period, which would be demand over 5 weeks, plus Z times the standard deviation of demand over that same 5-week period. So to make this simple, let's break these down into chunks and let's calculate this in stages. The first thing we need to do is we need to determine what is that lead time plus review period. And clearly, lead time is 3 weeks, review period is 2 weeks. So our lead time plus review period is 5 time periods, or 5 weeks. Then what is our mean demand during that 5 weeks? And that is the 5 weeks times our mean demand per week. So our average or mean demand over a 5-week period is about 718 boxes. That's about what we expect to consume over that 5-week period between one order being placed and the next order being received. Then we need to figure out, all right, that's the mean, what is the standard deviation? And the standard deviation will be the standard deviation of weekly demand times the square root of the number of time periods or weeks. So we'll always use the number of time periods, we'll use the square root, and that will give us the standard deviation of demand over a 5-week period. Next, we have to multiply this number, our standard deviation. We have to carry a multiple of those as safety stock, and that multiple is the Z value. And again, this will depend on our probability. If we set it at 98%, our Z value will go up to 2.05. At 96% probability, we're going to multiply the Z value times our standard deviation. And so our safety stock is going to be just under 23 units. That is, again, that is the standard deviation of demand during lead time plus review period multiplied times our Z level to get to 96%. So our order up to level then is this figure. That's our cycle inventory. Plus this number, that's our safety inventory. Our order up to level will be the sum of those two. Cycle inventory plus safety inventory. Or 740.41. Now we have to be careful. We're going to round this off because we can't order percentages or calculate percentages of a box. However, anytime we're working with safety stock, you always have to round up. And here's why. We have decided that this is our maximum risk tolerance for running out of this box is 4%. So we want a 96% certainty. If we set our order up to level rounded down, we will be fractionally below our 96% service level. Service levels are something that we have to take very seriously. Service levels are in many cases, in many ways, strategic decisions for a company. So when we say we will tolerate a 4% stock out risk, that doesn't mean 4.25%. So we always round up safety inventory calculations. We round them up. So let's do that. We'll use the roundup function. And this then becomes 741. We've got this whipped now. All we have to do is we go out on our next Friday that it's time to order. We take stock and we determine that we have 560 on hand. This is our order up to level. This is how many we have. Our order quantity then becomes the difference. Whatever quantity it takes to add us back up to our max or our order up to level. So this would be our order quantity. And each time, every other Friday, each time we hit an order interval, we will order the quantity that it takes to bring us back up to this number. Hopefully this has been instructive. Hopefully it's clear. You have to practice with this a little bit before you're entirely comfortable with it. Thanks for watching.